Okay, so today we're going to start chapter 12 in the book, which deals with alcohols mainly as a functional group, all of their various reactions, all their various properties. And then we'll also talk about something called a phenol, which I'm going to introduce to you guys in a second. Okay, so alcohols as a functional group, if you guys remember back when we learned or tried to memorize all of our functional groups, were compounds that contained a hydroxyl group, right? So the hydroxyl group is this OH group. And again, with respect to alcohols, these are going to be compounds that have an sp3 hybridized carbon. So this is sp3 hybridized that is attached to an OH group. Okay, and so again, if we drew the Lewis structure, that oxygen has two lone pairs of electrons. It is bound to a hydrogen as well as an sp3 hybridized carbon. Okay, so that is the characteristic feature of our alcohol functional group. We do have a special type of alcohol that we will discuss in this chapter. So this is an alcohol or a hydroxyl group that is attached specifically to a phenyl ring, right? So this guy's an aromatic ring, a phenyl ring. Whenever you do have an alcohol or a hydroxyl group attached to a phenyl ring, that actually has its own name, its own type of compound, and it is called a phenol. Again, the phenyl being the phen, and then the OH being the OL. You also know that you're dealing with an alcohol as a functional group in your compound if the ending of the compound ends in OL or ol. Okay, so anytime we move into talking about a new functional group, the first thing we always have to do is learn how to name them. So we're going to go through just briefly talking about how we're going to name alcohols using our IUPAC rules for nomenclature. Specifically, we're just going to deal with how this differs from what we've been dealing with before, and then we'll move on to other aspects of alcohols. Okay, so as a reminder, every time we try to name something, we use the same four basic steps, right? The first one being identifying the parent chain. Then we're going to identify the substituents. We're going to number the chain, and then we're going to symbol everything alphabetically. Okay, so now what differs with respect to alcohol compared to what we've dealt with before, right? So as a reminder, when we're identifying the parent chain and we were dealing with alkanes, right? So again, alkanes were just carbon, hydrogen, single bonds. When we were looking for the parent chain for alkanes, we were looking for the longest consecutive carbon chain, right? When we moved on to alkenes, right, we were looking for the longest consecutive carbon chain that contained the double bond, and we saw the same exact thing for alkynes, right, for the triple bond. Okay, so for alcohols, we're going to be doing very similar things with respect to the alkenes and the alkynes, in that the parent chain is going to be the longest consecutive carbon chain that has the carbon attached to the OH group, to the hydroxyl group, right? So for example, if we had a compound here that was an alkane, and we were looking for the parent chain, we'd be looking for the longest consecutive carbon chain. This guy would give us 8, so we'd have octanol or octane. If instead we had an OH group, a hydroxyl group present in that compound, instead of that parent chain being the longest consecutive carbon chain, it is instead going to be the longest chain that contains the OH group, right? So for this guy, it'd be 1, 2, 3, 4, 5, 6 carbons, right? The last carbon has that OH group attached. So because that is the longest chain that contains the OH group, that is going to be our parent chain, okay? Another way that this differs with respect to identifying and naming the parent is that, again, this is 6, so our base here is going to be hex. With respect to alkanes, the ending is always A-N-E. It's really moving a lot today. But now what's going to change with respect to alcohols is instead of the E ending, we're going to remove this guy and we're going to replace it with an ol. Okay, so hexane would have been the thing for an alkane, but now we're going to leave off or remove that E as an ending because it has an OH as a functional group, and it's going to end in ol here. Okay, so second step in this is identifying substituents. That's not going to change, right? The alcohol is a part of the parent, so don't try to consider it a substituent. But for the rest of them, all other types of substituents, they're all going to be fairly similar. The other thing that's going to change comparatively to what we know is numbering the chain, right? So assigning locates. Again, with alkanes, we numbered the chain so that our substituents got the lowest number possible. With alkenes and alkynes, we numbered it so that the double or triple bond got the lowest number possible, right? And again, we're going to see a very similar thing with respect to alcohols, right? So now when we number the parent chain, we're going to give the OH group the lowest number possible, right? So kind of like if we're keeping track of priorities here, the alcohol is going to trump, in terms of priorities, the alkene, which is going to, or the alkyne, which then trumps the alkene, right? So when we're trying to number things, alcohol right now is going to take preference over everything else. So for example, for that, for this compound, we've got 1 carbon, 2 carbon, 3 carbon, 4, 5, 6, 7. So 7 is hept as a parent. Again, we're going to number this so that the OH group gets the lowest number possible. So this is 1, 2, 3, 4, 5, 6, 7. If alkenes, if the double bond took preference, then we would start it over here. But again, it does not, so we're not going to do that. And now if I wanted to go ahead and assemble this guy, at least for the parent chain, I would note my 2 methyl groups, my 3 methyl groups here. So this is a methyl. We've got 2 methyls here. So we would say if we were going to assemble this guy, this is going to be a 5, 5, what is that last one? 6 trimethyl. But then as we move into the parent chain, the base of it is going to be hept. But now you have 2 functional groups that are in that parent chain. Again, we give this guy ENE, we give this guy OL. So the OL is going to end it. So because of that, we're going to say, okay, this is going to be where the double bond starts. So this is 6-ene. We leave off the E and then dash 2-ol. And again, I only wanted to, kind of illustrate that assembly with respect to having a double bond as well as an alcohol in the same parent, for how to actually arrange that. So the ol is going to go at the end, the alcohol goes at the end because it has a higher priority, but we still have to identify that double bond, so that's going to be 6-ene to ol. Okay, so then other things to consider. If you have a cyclic alkane that contains the hydroxyl functional group, you're going to number that chain so that the OH gets the lowest number possible. Again, kind of similar to what we just saw with numbering the chain. The only reason why we mentioned this is when we had cyclic alkanes before, we always wanted to number it so that the substituents got the lowest number possible, right? So if this wasn't an OH group and was like, let's just say a methyl group, then we would have numbered this 1, 2, 3 because both of these guys would have gotten the 1. But that does not matter anymore, right? So now we're always going to number it so that the alcohol gets the lowest number possible. That will always be 1 in these type of cyclic groups, and then everything else will go from there, right? So again, we number this 1, 2, 3 because if we'd gone the other way, 2, 3, 4, that would have given these 2 methyl substituents a 4. If we went this way instead, it would have given them a 3. So the whole purpose of this is that alcohols always are going to get the 1 position, and then everything else is going to get based on numbering it the lowest number possible. Okay, so then you should also be aware of a couple of common alcohols that don't go by their IUPAC name, or they will have an IUPAC name, but they're not usually referred to as that. So one of those is isopropyl alcohol or isopropanol. If we were actually to name this via IUPAC nomenclature, this is 1, 2, 3. So this is 2-propanol. But again, like you don't really hear about 2-propanol. You usually hear about isopropyl alcohol, right? Another very common one for that is tert-butyl alcohol. Again, this would be a 2-methyl-2-propanol as the actual IUPAC name, but its common name is much I guess, is referred to much more often, which again is tert-butyl alcohol. For these guys, they should be kind of common at this point in time for the world we're living in right now. So everyone's looking for isopropyl alcohol, but most people can't find it. Same thing with tert-butyl alcohol. These are great antiseptics. Unfortunately, they're very difficult to find at this point in time. And then with respect to the structure of alcohol and how we can refer to them, we will also see this follow a very similar theme with respect to what we saw with alkyl halides. Right, so for example, if we had a carbon that had a chlorine, and that carbon sp3 hybridized was surrounded by all hydrogens, we would call this a methyl alkyl halide. If instead we had one of those hydrogens replaced with another alkyl chain, and again this was going to be an alkyl halide, then this became a primary alkyl halide. If we replace another hydrogen with another alkyl chain in secondary, and then finally tertiary, if all of them are alkyl chains, we see the exact same thing for alcohols, right? So the carbon that the OH group, the hydroxyl group, is attached to is called the alpha carbon. And then the amount of substituents that are around it are going to determine its primary, secondary, tertiary structure, right? So if one of the things that this alpha carbon is attached to is an alkyl group, it's a primary alcohol. If two of them are alkyl groups, it's a secondary alcohol. And then if all three of the things that are attached to that alpha carbon are alkyl groups, this is a tertiary alcohol. Same thing, this would also be if we had a carbon attached to a hydroxyl group, and then all of the surroundings were hydrogens, and this would be a methyl alcohol, or more importantly, this would just be methanol. Okay, so we're going to do an example, and then I'll let you guys have a few to work on your own. Again, we're going to follow the exact same protocols that we have been thus far in determining the correct IUPAC name for this compound. Okay, so first off, we're going to look for the parent chain. And the parent chain is going to be the longest consecutive carbon chain that contains the OH group. Our OH group is right here, so that's why we know it's an alcohol. So if we started over here, we'd have 1, 2, 3, 4, 5, 6, 7, 8. That would give us 8. If instead we started over here, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. And so 9 is the longest chain that contains the carbon, the longest consecutive carbon chain that contains the hydroxyl functional group. So 9 is our parent chain. If you guys remember, 9 is non, and then this is an alcohol, so this is going to be nonane without the EOL. Let me actually write that a little bit better. So nonanol. Okay, so that's number 1, identifying the parent, naming it. Number 2, we're going to look for substituents here. So this is going to be anything that branches off the parent chain. So first one, we've got a 1,2 carbon chain. So as a reminder, that's an ethyl group. And then we do have 2 halogens here. We have 2 chlorines. So we refer to those as chloros, and we treat those as substituents. So those are our 3 substituents, essentially. So then the third step is numbering the chain. All right, again, we want to number this so that the OH gets the lowest number possible. If we started up here, that would give 1, 2, 3, 4, 5, 6, 7. The OH is 7, which is bad. We don't want to do that. If instead we started over here, we'd give it 1, 2, a 3. So this is going to be the best way to name or to number it. 4, 5, 6, 7, 8, and then this becomes a 9. And now we're ready to move on to step 4, which is a symbol. But there is one thing that we haven't really looked at. So anytime we have chirality centers, we also have to assign those guys absolute configuration, if you guys remember back in the day. So for chirality centers here, we have sp3 hybridized carbon here that has 4 unique groups attached to it. We also have an sp3 hybridized carbon here that has 4 unique groups attached to it. So both of those guys are chirality centers that have to be, or their configuration has to be specified. So I'm going to deal with carbon 3 first. So I'm just going to redraw the base structure. And then I've got my wedge and then my dash. And I'm just going to number it based off of this. Okay, so when I'm looking at that, I'm looking at an OH. That hydrogen is implied, so that guy is coming out here. Then we've got a carbon and we've got a carbon. When I'm prioritizing these guys, I want the thing that has the highest atomic weight to come first. That if I'm comparing a hydrogen versus an oxygen versus a carbon, that's going to be oxygen. So this one is going to get number 1, and that's on my dash here. Hydrogen is the least, so we don't have to worry about it. It's going to get number 4. But then when we come out to carbon versus carbon, there's a tie. So now we have to move out from these carbons. This carbon is attached to a carbon and then 2 hydrogens, whereas this carbon is attached to a carbon and then 2 chlorines. So chlorine, a chlorine, and a carbon. The chlorine versus the carbon, let me illustrate that. This versus this, chlorine gets, or chlorine trumps, I guess, a carbon. It's got like an atomic mass of 35 versus 12. So that guy will get number 2, and this guy will get number 3. So then from there, I need to rotate this so that the 4 goes into the dash. And so to do that, I'll go ahead and switch these 2 positions. So this will be 1, this will be 4. If I've done that, I have inverted configuration, so I have to also switch these 2. So this becomes 2 and 3. And then in moving from 1 to 2 to 3, we have clockwise rotation. So this guy ends up being R. I also have to do the same thing for carbon 6 here. So for carbon 6, again, we'll go ahead and draw the dash. The hydrogen is on the dash, so we know that's going to be 4. And trying to determine who's 1 versus 2 versus 3, again, we have a kind of a tie here. We have a carbon, we've got a carbon, we've got a carbon. So now we have to move out. This carbon is attached to a carbon, hydrogen, hydrogen. This carbon is attached to a carbon, hydrogen, hydrogen. This carbon is also attached to a carbon, hydrogen, hydrogen. So that's a tie there. We have to move out again. So I'll move out to the next one. So this guy versus this guy versus this guy now. So this guy's attached to a chlorine, and a carbon. This guy's attached to a carbon, hydrogen, hydrogen. This guy's attached to just a hydrogen, hydrogen, hydrogen. All right, so obviously chlorine is going to trump a carbon, which is going to trump a hydrogen. So we can determine the numbering from there. So we have 1, we have 2, we have 3. And we don't have to rotate anything because 4 is already on the dash. So I'm getting from 1 to 2 to 3. We are also moving the clockwise direction, so we are also R at carbon 6. Okay, so then once we've done that, we're ready to assemble. The chirality centers come first, right? They come in parentheses. So we have to specify that this is 3R. This is separated from the second chirality center, which is 6 and also R. That's it. We're done with that. We have a letter. We're moving into a number, so we're going to use a dash. Now we're ready to identify our substituents. So we have chloros and we have an ethyl. So again, we're arranging everything alphabetically. Chloro would come first. There are 2 of them, so it's going to be a dichloro, and they're both at the 4,4, dichloro. Now again, we have to identify our second substituent, which is that ethyl group. This ends up being 6-ethyl. And then we're moving into the parent chain. The parent chain was nonane. So nonane. And then we have to specify where the alcohol is. It is at carbon 3. So nonane 3-ol. Again, you could have also said 3R, 6R, 4,4, dichloro, 6-ethyl, 3-nonanol. That is the old convention. This ideally is going to be the way to go, though, because if we have more than one functional group, right, if we had like an alkene, a double bond in that parent chain, or a triple bond, it would be hard to specify using this old convention. Okay, so again, it is any type of stereochemistry, it is substituents, and then we move into the parent chain, and right before the ending, we specify where that alcohol is from the parent, separated by the ol. All right, so go ahead and give these guys a shot. Come back for the answers. I don't think I'll spend much time going over specifically how to name them, but try these and then hopefully you get the correct answer. So pause the video and then push play when you're ready. Okay, so I'm going to start with A. So the first one, again, we're going to look at identifying the parent chain. Parent chain has to contain the carbons attached to the hydroxyl group. So we have 1, 2, 3, 4, 5. There's no other way we can really get more carbons than that has the carbon attached to the OH group. So our parent chain is 5 carbons. And again, the base for that is pent. But again, this is an alcohol, so we have pentan and then OL at the end. So after a parent, we can look at our substituents. We've got a couple. We've got a methyl, we've got a methyl, we've got a methyl. All right, so these guys are all methyls. There's 3 of them, so we've got a trimethyl. Now we're going to number. Again, we want to number so that the OH gets the lowest number possible. We're going to start at this carbon. We have 1, 2, 3, 4, 5. And so now we're ready to start assembling. So our substituents are going to come first. We've got a 2, a 3, and a 4. So this is 2, 3, 4, trimethyl. And then we move into our parent. We have pentan, and then we have to specify where the alcohol is. It's at the 1 position, so pentan 1 ol. Now the only thing left to do is identify the chirality centers, right? So in here we've got a chirality center here, we've got a chirality center here, so we have to specify configuration for those two. So I'll start with carbon 3. So if we redraw this, we've got a 4 or hydrogen on the dash, so that's going to be our 4. We're trying to figure out 1 versus 2 versus 3. We've got a carbon, carbon, carbon. That's a tie. So then we move out to what's attached to that. This guy is a hydrogen, hydrogen, hydrogen. This guy's got a carbon, carbon, hydrogen. This guy's got a carbon, carbon, hydrogen. So we move out again. So now we're looking at this versus this. This guy's already been trumped, so this is going to be 3. So then here we've got a guy attached to an oxygen, hydrogen, hydrogen, and then this guy is attached to a hydrogen, hydrogen, hydrogen. So this oxygen is going to trump. We've got 1 here and 2. So then I'm getting from 1 to 2 to 3. We're moving in a counterclockwise direction, so this guy is S. And then finally carbon 2, if we do that one quickly, again, the dash is a hydrogen here. So we've got 4 on the dash. We've got carbons again. Again, as we move out, we have carbon, carbon, carbon. That's a tie. This guy's all hydrogens, though, whereas this guy's an oxygen, hydrogen, right? So we have an oxygen that's going to trump everything. This will be 1. This will be 2 because this guy's attached to a carbon. Again, this guy's are attached all to hydrogen, so this is 3. So I'm going from 1 to 2 to 3. Oh gosh, I do this all the time. This is counterclockwise, right? So this is S, but this motion is clockwise. So this is R. Oops, R. Okay, so then at the end, we're going to include that. We've got a 2S, and then we've got a 3R dash 2, 3, 4 trimethyl pentane 1 ol. And let me just erase this so that nobody gets confused and hates me and emails me that I was wrong. That is R, and this was S. And if I am wrong, just let me know. You can email me. Please feel free. I could be confused even at this point in time. Okay, so then B, we've got a cyclic alkane or cyclic alkanol, a cyclohexanol essentially in here. Oh, I forgot that. Yeah. So again, with these cyclic compounds, we're looking for the ring that contains essentially the OH group. If we look at this, we've got 1, 2, 3, 4, 5, 6. So the base here is 6 carbons, which is hex. We have hexane, all. But as a reminder, and this may not have been on the top of your mind, because it's cyclic, we have to specify that with that cyclo prefix. All right, so this is cyclohexanol as our parent. If we look for our substituents, we've got 4 of them. We've got a methyl, 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 right? So we've got a tetramethyl. Now we need to number. Again, we said 1 has to be the alcohol. So now which way we go, either this way or this way, is going to depend on the other substituents. If we go to the right here, then we would be at 4 for these guys. That would be our next substituents. Whereas if we went to the left, we would give 2 to these guys. So again, we want to give our substituents the lowest number possible. So we're going to number this going left or counterclockwise. So this is 3, 4, 5, 6. So now we've got a 2, 2, 4, 4 tetramethyl. And then cyclo hexane -1 all. Again, we have to specify where the alcohol is at the ending there. Now, the only thing that we haven't done here is, again, identify the configuration about this chirality center. So if we quickly move this guy down here, we've got the OH on the wedge. There's a hydrogen on the dash, so that's easy to see. It's 1 and 4. As we move out, we've got a carbon attached to hydrogen and carbon, or we've got a carbon attached to 3 carbons. So this carbon will get 2, this will get 3. So we've got 2, 3, and again, getting from 1 to 2 to 3, we are moving in a counterclockwise direction. So this is S, and we will specify that at the beginning with S in parentheses. Okay, so hopefully you guys got those, and that was a nice, just quick refresher on nomenclature. Okay, so after nomenclature, we usually talk about some physical and chemical properties of whatever type of functional group we're dealing with. All right, so a reminder, what we mean about physical properties, we're talking about things like boiling point and melting point, etc. The thing most important that really influences the boiling point or the melting point or any of these physical properties that a molecule has are intermolecular forces, right? So when we're talking about this stuff, we're talking about intermolecular forces, and this is frequently abbreviated IMF. And so we had talked about intermolecular forces like back in first semester, like chapter 2, right, I think, or chapter 1, I can't remember, right? Now, as a reminder with respect to intermolecular forces, we're looking at the attraction or the forces that exist between molecules of the same type, right? So, for example, if we have molecule A and we have another molecule A over here, we're looking at the forces that exist between these two molecules, right? What things are holding them together or breaking them apart. And we had a couple of different intermolecular forces that were going to influence how strong this attraction was, right? Overall, the stronger this attraction, the stronger the intermolecular force between molecules, the larger the boiling point, larger melting point, because again, you needed more energy to break the interaction, the force between different molecules, right? Now, with respect to intermolecular forces, we had a couple, right? So the first one that we talked about was dispersion. All molecules have dispersion. We also call this a fleeting dipole. And again, this was kind of a weak force, but it depended on the ability of electrons to kind of all of a sudden unevenly distribute themselves in a molecule. And so by doing that, that would essentially induce the same thing in another molecule. It'd leave this partial negative, this partial positive, and that would be the interaction, the intermolecular force between things. Another type of intermolecular force was dipole. Right, so dipole force, this is for molecules that actually had polar bonds in them. So we had polar bonds in the molecule. And again, those polar bonds created a dipole moment, and that it was the interaction of those dipole moments, those partial positive and partial negatives, that was giving rise to this interaction, this intermolecular force. And then the final one that we really talked about was hydrogen bonding. And so hydrogen bonding was a special type of dipole. It's when you had a hydrogen that was bound to a small electronegative element like oxygen or nitrogen or fluorine. And again, this was like the strongest of the intermolecular forces that we talked about, right? So as we go from dispersion to dipole to hydrogen bonding, we're increasing our intermolecular force. So we're increasing the boiling point, increasing the melting point of a compound, right? So essentially with respect to alcohols, because of that hydroxyl group, right? Because of the hydroxyl group at the end, this is a hydrogen bond, right? So alcohols are capable of hydrogen bonding due to the presence of that hydroxyl group. Again, with respect to intermolecular forces, as we move from something like ethane, which essentially has, an alkyl chain attached to a hydrogen, the only intermolecular force that ethane has at its disposal is dispersion force, right? So it has a very low boiling point because of that. As we replace that hydrogen with the chlorine, with the same type of like carbon chain on the left, we increase the boiling point because now these guys have a polar bond, right? So this has a dipole moment. So this has dipole forces. Dipole forces are stronger than dispersion, so we just did an increase in boiling point. But if you compare that to something like ethanol, which again has the exact same hydrocarbon chain on the left, but now we've replaced that chlorine with a hydroxyl group, we see this drastic increase in boiling point because, again, ethanol is capable of hydrogen bonding, and hydrogen bonding is the strongest of our intermolecular force. So just as a reminder what hydrogen bonding looks like, right? This oxygen-hydrogen bond is polar, right? Oxygen pulls all the electron density towards it. So we get this partial negative that forms on it. We get this partial positive that forms on the hydrogen. The reason why it's so much stronger than just normal dipole is because these hydrogens are small and they can get really, really, really close to the partial negative or the lone pair of electrons on the oxygen of another molecule. All right, so again, a hydrogen bond would look like one molecule of our ethanol, and it would be interacting with another molecule over here, let's say. So we have this guy, and again, this will just be our ethanol or R group. This has the exact same partial positive, partial negative, and this partial positive is attracted to this partial negative, the lone pair on the oxygen, right? So this is the actual hydrogen bond that we discuss here. Okay, so because alcohols have or possess this hydrogen bonding, they, or at least some of them, are what are said to be miscible in things like water, right? So water is like this perfect hydrogen bond vehicle. So for each water molecule, you get a hydrogen bond, at least 4 different hydrogen bonds possible. Water is also very polar, right? So because it's polar, it's going to dissolve anything that is also polar. With respect to alcohols, though, there are essentially going to be 2 different portions of the molecule. There's going to be things that are polar, which is the hydrogen bonding region, that hydroxyl group, and then there's also going to be a hydrocarbon chain that's attached to it, right? So we call this a hydrophilic region, which is the hydroxyl group, and then we can call it the hydrophobic region, which would be that hydrocarbon chain. And so again, a lot of alcohols are soluble in water, right? And that's because the hydrophilic region is participating more, or is not as affected as much as the hydrophobic region, right? So things like methanol, right? So methanol is this guy. Methanol is completely soluble. Man, I'm getting real bad here. Okay, so methanol is not soluble. It's actually completely miscible in water. So miscible, if something is miscible in something, it means that it is, or it can be mixed in any proportion and not separate in layers, right? So things like methanol, things like ethanol, things like propanol, again, all I'm doing here is increasing the hydrocarbon chain on the hydrophobic region. All of these guys are completely miscible in water, which means that you can mix them in any proportion and not get any type of separation in layers. So a really good example of that is what we would consider ethanol, right? So when we talk about alcohol and alcoholic drinks contain ethanol in them, right? But the majority of them contain ethanol in a mixture of water, right? So things like vodka, things like tequila, those are technically, yes, ethanol or alcohol based, but the ethanol proportion is only like 35% depending on the spirit. The remainder of that is water, right? And so anytime you're dealing with a percent, they're dealing with percent by volume. And so it's giving you an idea of how much ethanol is present in the compound. Again, the remainder of the compound is just going to be water. But if you think of things like Everclear ends up being like, I think 95%, or gets pretty close. And even in the lab, when we deal with ethanol, we utilize ethanol in the lab, it tends to be about 98% ethanol. Again, the remainder of that is just water. It's really hard to get 100% pure ethanol. Okay, so then as we increase that hydrocarbon chain, this miscibility actually starts to decrease, right? So you can still be miscible up to propanol, but the minute you get to butanol, so again, this is going to be 4 carbons attached to the alcohol group, we stop being miscible and instead we turn into a compound that is soluble. So butanol is soluble in water, but the difference between solubility and miscibility is if you're soluble, you can mix, but you can only mix to a certain amount, right? So if we had too much butanol in the solution, then instead of them mixing evenly, you would actually see the formation of 2 different layers, right? So butanol is soluble, it will mix evenly, but only to a certain amount. This continues as we increase the carbon chain onto octanol. So octanol is only very, very, very slightly soluble in water, right? You can only put a very small amount in and get equal mixing. But then when we move on to nonanol and decanol, so this is going to be 9 carbons and 10 carbons respectively, these guys are not soluble. So the minute you put a nonanol or a decanol, soluble. I should know not to try to spell and talk at the same time, but you know, these things. The minute you put a nonanol or a decanol into water, they will just separate into 2 separate layers. So they will not mix at all. Right, so methanol, ethanol, propanol, those guys are miscible. You can mix any amounts in them and they will evenly mix with water. They will not separate into layers. As you move into butanol, now you're dealing with a compound that is soluble in water, but not miscible. And again, solubility, they will mix in a certain amount, but at a certain point, you're going to start to see the separation of layers. This continues on to octanol, but as we move into nonanol and decanol, these guys end up not being soluble because now that hydrophobic hydrocarbon chain kind of outcompetes that hydrophilic hydroxyl region. And so we won't actually see any type of mixing for those guys. All right, so another thing to consider, instead of physical properties of alcohols, we need to start dealing with chemical properties of alcohols. And the first thing that we're going to consider is the acidity of alcohols, so how acidic an alcohol is. So as a reminder, we had a couple different ways to measure acidity. Again, this goes back to the first semester. Our quantitative method of measuring acidity was pKa values, right? So overall, the lower the pKa, the stronger the acid. And again, this was lower pKa, so therefore the higher the pKa, the weaker the acid. And we're talking about acidity again, it's this ability to donate a proton to something else, right? So this is our quantitative measure. We also had a qualitative measure, right? And that was comparing the stability of the conjugate base, right? So we had our acid, Its conjugate base was, again, that acid with the hydrogen removed that had a negative charge, right? So we have our acid and our conjugate base. We could kind of compare the stability of this guy using a couple of different means to determine the overall acid strength, right? So the more stability we had in the conjugate base, the overall stronger the acid. And then kind of vice versa, right? The less stable the conjugate base, the weaker the acid, but also the stronger the base itself, okay? And so we had a way to do that. We utilized that little acronym AREO to kind of understand this. So remember, A stood for atom. And so when we're looking at alcohol and their acidity, or alcohols and their acidity, let's say we have just some sort of common alcohol here. This could be ethanol, this could be methanol, whatever. Again, we're considering the acidity of this, and what we're considering is how easy is it to get rid of this proton. To kind of understand that, again, we can imagine some sort of strong base coming along, taking this proton, leaving behind these electrons. We're going to determine the strength of this guy by looking at the stability of this guy, the conjugate base, okay? Now, there is actually a term for these with respect to alcohols, right? So again, if this is an alcohol, the deprotonated conjugate base of that alcohol is called an alkoxide ion. So for example, if this was ethanol, let's just do methanol because that's easy, or we can just draw the bond line structure. So if this was ethanol, then the conjugate base, deprotonated conjugate base of this guy, which looks like this, is called F-oxide. Same thing with if it was methanol, it'd be methoxide. Terbutanol, it's terbutoxide. Right, so anytime we're dealing with that deprotonated conjugate base, it's an alkoxide ion. All right, so again, atom dealt with whatever the atom was that the negative charge lied on. So for any alcohol, that atom is always going to be on oxygen, right? And again, we could kind of determine the stability of this by looking at where it was on the periodic table, right? So the more electronegative the element, the better it was at stabilizing that negative charge, the more stable it was, right? So if we look at the periodic table as we go from left to right in row 2, we've got carbon versus nitrogen versus oxygen versus the halogens, right? So this, let's say, is fluorine. As we move from left to right, we're going to increase in electronegativity. And so things on the right over here are going to be much better and much more able to stabilize that negative charge that develops on the conjugate base compared to things on the left. So because of that, alcohols are going to be more acidic, right? Because again, oxygen is going to be better at stabilizing that negative charge than things like amines or any type of hydrocarbon. Because again, it's going to be better at stabilizing that than nitrogen or carbon, but it's going to be less acidic than any of the alkyl halides, but it's going to be less acidic than any of the hydrogen halides, right? So any of the HFs, the hydrofluorics, the hydrochlorics, any of those guys. And again, we can determine that just by looking at the stability of that conjugate base. We can also do it by pKa because again, the pKa's are listed. All right, so if we wanted to deprotonate an alcohol to form our ethoxide or our alkoxide ion, we can do that if we use a stronger, let's just say a stronger base than the ethoxide or alkoxide itself, right? So things that are stronger bases are things like hydrides, right? So this is a negative charge hydrogen. So if you put hydride in the presence of ethanol, you would produce this ethoxide. Other things that can do this are metals like lithium, potassium, etc. They are capable of deprotonating usually any type of alcohol to produce that alkoxide ion. Okay, so other factors that are going to essentially affect the acidity of alcohols as well as phenols. So A stood for atom, right? But then R stood for resonance. We talked about this when we talked about areo. I stood for induction, and O stood for orbital. So if we consider two alcohols, right? So cyclohexanol versus phenol. And again, we're trying to consider which one of these two is the stronger acid. To do that, we're going to look at the stability of the conjugate base. If we deprotonate cyclohexanol, we end up with, oops, that's really ugly. Why am I doing that? I'm not quite sure what's happening with my brain right now. So if we deprotonate cyclohexanol, we're going to end up with cyclohexoxide as an ion. And if we deprotonate phenol, we're going to end up with the phenoxide ion, which looks like this, negative charge. Again, if we were trying to figure out who was more stable, right, therefore who was the stronger acid, we'd look at atom first. For both of these guys, the atom is oxygen, so that's not going to help us. But now for phenoxide, if we move into resonance, there are a lot of different resonance forms for this phenoxide ion, right? So the first one that we could draw, we could form a double bond between the oxygen and carbon. As a result of that, these electrons have to move to this carbon, right? So if we draw out all the various resonance structures for this phenoxide ion, we'll find that there's like 5 or 6 different resonance structures, right? And again, as a reminder, with respect to resonance, the more resonance structures you can draw for a compound, the more stable it is, right? The more dispersed that negative charge is throughout the entire structure. So again, if we continued on this, there'd be another pattern here where we could draw this guy, so on and so forth. For this cyclohexoxide, right, there are no resonance structures. So because of that, because phenoxide has all of these various resonance structures, and we don't see that with this deprotonated cyclohexanol, phenoxide is a much more stable conjugate base, meaning that phenol is much more acidic. I don't even know why I wrote much, but much more acidic comparatively to cyclohexanol, okay? And again, you can compare that or determine that using pKa values if they are given to you. Now, the acidity of phenol, because of all of this resonance stabilization, and let me go ahead and resonance stabilization, is actually why we treat phenol differently than just an alcohol, right? So alcohols tend to be not super acidic, right? Depending on what you're dealing with. Like, they're going to be more acidic than amines. They're going to be more acidic than carbon-containing compounds. But comparatively, they're not super acidic. Phenol is fairly acidic, though, right? And so that's why we're actually going to treat phenols differently, and we kind of give them their own separate structure because of that, or their own separate section because of this difference in acidity comparatively, due to the resonance stabilization of the phenol group. Okay, so another thing to consider is induction, right? So if we compare ethanol to trichloroethanol, induction has to deal with this electron withdrawing groups, right? So these polar bonds that form. Again, if we were trying to say who is more acidic, we'd be comparing ethoxide versus this trichloroethoxide versus this guy with respect to determining who is more stable. These chlorines to carbon, these are polar bonds, right? Chlorine's much more electronegative than carbon. So these guys pull all this electron density towards themselves. That leaves behind this partial positive kind of in this region of the molecule. And this partial positive is going to help stabilize this partial negative, or this full negative charge that develops on this conjugate base, right? So because these guys are electron withdrawing, they're pulling all this electron density towards them, it allows this negative charge to be shared over multiple atoms, or to be at least a little bit more stabilized, because it's like pulling essentially that electron density away from the negative charge on oxygen. So because of that, this is more stable than a compound that doesn't have that induction or doesn't have those electron withdrawing groups on it, right? So because this is more stable, this is more acidic, And again, we would utilize a Rio to figure that out, right? If we looked at the negative charge, they were both on oxygen. That wasn't going to tell us anything. There was no resonance structure. So now this guy happens to be more acidic because, again, of that induction. The last one is orbital. We're not going to consider that because it doesn't matter. But then the other thing that we never talk about, which I wish they would say it's a Rios, right? Because solvent effects do matter. Has to do with, again, the solvent effects and how solvent is able to get in and stabilize a negative charge that develops in these conjugate bases, right? So again, if we had something like ethanol versus terbutanol, ethanol, negative charge is again going to be on that oxygen atom. Same thing with terbutanol, negative charge is going to be on that oxygen atom. There is no induction, there is no resonance, and we don't care about orbital, right? So now the only thing that's going to really affect these guys and their differing acidities or their differing stabilities is the ability of solvent to get in and help stabilize that negative charge. So if solvent was something like water, right? Again, water has hydrogen bonding. We get a partial negative on the oxygen, a partial positive on the hydrogens. The ability for this guy to get in here and help stabilize that is going to determine how stable this thing overall is, right? Now, if we think about ethanol, ethanol is completely unhindered, right? So solvent molecules are really able to get in and help stabilize that negative charge on all sides with respect to ethanol. Terbutanol is a little bit different because, again, it's got these big bulky groups attached to it, right? That's going to hinder the ability of solvent molecules to get in here and help stabilize that negative charge on the oxygen. Okay, so the better able solvent is at getting in and stabilizing the negative charge that develops on the conjugate base, the more stable the conjugate base energetically, and therefore the stronger the acid. Right, so that's better with respect to ethanol because it's not bulky, it's not big. It's worse with respect to terbutanol because it is bulky and it is big. Solvent isn't able to get in there and help stabilize that negative charge as well comparatively to ethanol. So oxide is more stable than terbutoxide. Ethanol is a stronger acid than terbutanol. Okay, so an example of a question that you could see here. The question here is which of the following two compounds is more acidic? Again, we're dealing with alcohols, so we're trying to determine, using our little qualitative approach, who is the stronger acid between these two alcohols. And again, to do that, we're going to compare the stability of the conjugate bases, right? So the first thing I'm going to do is I'm going to imagine some sort of base coming in here, taking off that proton, leaving behind those electrons on that oxygen. And I'm going to redraw the two conjugate bases that result as a result of that deprotonation, right? So we'll have an oxygen with a negative charge here, and I'll go ahead and draw the lone pairs. We've got a double bond here, and we've got an oxygen here. We do the same exact thing over for the compound on the right. So we're going to end up with an oxygen with a negative charge and double bond over here. Okay, so again, the first thing that we're looking at is oxygen, or the atom. That's not going to change for either of these guys because, again, it's going to be on oxygen for both. So that's not going to help us determine who is more stable. As we move on, though, the next one is resonance, right? And so if we think about, are there any type of resonance structures that we can draw for molecule, we'll call this A over here, versus B, there is resonance that we can draw. There are resonance structures, right? So right now we have a lone pair in an allylic position. I want to make this prettier. We have a lone pair in an allylic position to a double bond, right? So one structure that we can draw is the lone pairs moving to form a double bond between carbon and oxygen. That's going to move the electrons up in this pi bond to this carbon. So the resonance form for this guy is a double bond here. We've got a lone pair of electrons on a carbon, a double bond here. Again, we have a lone pair in an allylic position, so another resonance form that we could draw is forming this double bond here and shifting these electrons up. Right, so that we end up with a double bond, and then a negative charge over here. So for this conjugate base, there are three resonance structures that we can draw for it. And so overall, this is fairly resonance stabilized. As we move over to this guy, we look for resonance structures here. There aren't any, right? We have a lone pair of electrons on the oxygen, but that's not allylic to a double bond, right? To be allylic to a double bond, you need to be adjacent to that double bond. Our only double bond for this guy is over here. So for this guy, there are no resonance structures. And so that's not going to at least be able to have that resonance stabilization. So then after resonance is induction. There's no difference with respect. There's no electron withdrawing groups. And then finally, we can consider solvent effects. But again, these guys are pretty much the same. The only difference between them was that double bond presence here and here. Okay. So because of this, this guy, because of this resonance stabilization, is a more stable conjugate base. Since it's more stable than this guy, this other conjugate base, B, then the acid that it derived from is more acidic. All right, so you say which of the two compounds is more acidic, A or B? The answer here is A, because of that resonance stabilization of the conjugate base. Okay, so go ahead and try these two. So I have two different problems here. I want to know which of the two following compounds is more acidic. We have phenol versus this tetrachlorophenol. And then we've got 7 heptanol versus, what is that? I don't even know. It looks like some sort of sea creature with an alcohol group. So we've got 5. So a 3-ethyl pentanol, pentane 3-ol, that would be the name for it, versus heptanol. So again, we're looking for, between these two, which one is more acidic. So go ahead, give these a try. I would also maybe kind of come up with a reason why you think one is more acidic than the other, going back to AREO, and then come back and hopefully I'll be able to answer which one is more acidic. Okay, so we're going to go ahead. We'll start with A here. Again, we're going to look at the conjugate bases of both of them. So the conjugate base of phenol is phenoxide. I'm going to just draw the negative charge. And then the conjugate base of the second compound, I don't know, we'll call this 1, we'll call this 2, is, what is it, tetrachlorophenoxide? Great. So we've got the negative charge here. We've got a bunch of chlorines around this guy. Chlorine, 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 and then we've got our phenyl ring, okay? Now, for both of these guys, we can draw a bunch of resonance structures, right? So both of them are going to have that exact same aromatic ring resonance stabilization that we looked at with respect to the phenoxide ion. The only difference here comes in the fact that we find a lot of induction with molecule 2 here, right? It has a lot of electron withdrawing groups, these chlorines. And so because of that, because of induction, in the presence of those chlorines are going to pull that electron density towards itself. So again, we're going to be spreading out electron density more in molecule 2 versus molecule 1, right? So this guy did have resonance, but no induction. This guy had resonance, but yes, induction. And so because of that induction, this is more stable. And therefore, this is the stronger acid. And then for B, again, we'll go with 1 and 2. We've got heptanol versus that thing, that jellyfish or octopus looking thing, all right? So for this one, this is not going to have to do with atom because it's going to, again, both be on let's see, we've got 3 peaks. We're going to have the negative charge on oxygen. Here, we're also, here, we're also going to have, actually, there is a name for this guy. I don't remember what it is, though. We're also going to have the negative charge on oxygen, so atom's not going to do anything. There is no resonance structures. There is no electron withdrawing groups. The only difference here is like one of them's bunched up. It has the same number of carbons, the other one is spread out, right? And the only thing that's going to affect overall is the ability of solvent to get in and help stabilize, right? So again, this thing's nice. It's spread out. Solvent can come in. We can just write solvent, right? Can come in on this side and come in on this side and come in on this side because hydrogens are tiny. They don't affect it at all. So solvent's going to help stabilize this conjugate base a lot more than this conjugate base because here we have all this branching, right? So all these big bulky groups. And so because of that, solvent's only going to be able to come in from this side to help stabilize. It's not necessarily going to be able to come in over here. So this one, because it's nice and linear and spread out, is going to have solvent stabilization more. So it's going to be more stable than this guy because, again, it's not branched. Yeah, I guess branched. It's all clunky. It's got a lot of sterically hindered groups around it. It's not going to let solvent get in and help stabilize it as well. So since this is more stable, this would be the stronger acid. And again, the reasoning behind that would be solvent effects, right? The deprotonated conjugate basis of heptanol, heptoxide, is not sterically hindered, so solvent can get in and help stabilize it a lot more comparatively to the weird-looking thing on the right. Okay, so now that we've gone over nomenclature of alcohols, both physical as well as chemical properties, in terms of acidity, we're now going to start talking about different ways that we can make alcohols with different starting materials, okay? So you guys should, we haven't really considered it in this manner thus far, but we do have a couple of reactions already where we could take something and make an alcohol from it, right? So if we go all the way back to our substitution reactions, so both SN2 as well as SN1 reactions, we can prepare alcohols from alkyl halides, right? So let's say that we had an alkyl halide, something like this. If we took a nice nucleophile like hydroxide, that nucleophile would attack our alpha carbon, kicking off our leaving group and producing an alcohol, right? So again, this concerted reaction, this SN2 reaction, was only good for methyl and primary alkyl halides when we were using hydroxide as our nucleophile, right? If we had moved up to secondary or tertiary alkyl halides, this hydroxide would not have acted as a nucleophile. So again, this is our nucleophile. Instead, it would have acted as a base, right? And so if we were using hydroxide ions for secondary or tertiary alkyl halides, it would have instead given the E2 the elimination product, right? So if we wanted to prepare an alcohol using that concerted bimolecular SN2 reaction, we could do that using hydroxide as a nucleophile, but this had to be a methyl or a primary alkyl halide that we were actually doing that on, okay? Unfortunately for but for a secondary alkyl halide, we don't really have a means by which we can solely prepare the alcohol, right, the substituted product as opposed to the E2 product. But for a tertiary alkyl halide, we could instead use an SN1 based mechanism, right? So if it's tertiary, it goes through that stepwise mechanism, right? We move through that carbocation intermediate, and we could always promote the SN1 reaction by using a weak nucleophile, right? So if we wanted to produce an alcohol on a tertiary alkyl halide, we could use a weak nucleophile like water, right? Again, this would have multiple different steps in the mechanism. You'd have loss of leaving group, you'd have nucleophilic attack, and then because our nucleophile is neutral, because it's water, there would have to be a proton transfer step at the end so that we'd end up with our deprotonated alcohol as our product, okay? So again, if you wanted to make an alcohol via substitution reaction with an alkyl halide, with a primary alkyl halide, you could go through the SN2 using sodium hydroxide as your nucleophile. If you have a tertiary alkyl halide, you could use water as your nucleophile and get your alcohol. And you could also use this as a methyl alkyl halide with respect to SN2. Okay, so that's one way that we've learned that we can make alcohols, right? If we have an alkyl halide initially, we can make an alcohol. Depending on the structure of the alkyl halide, it's going to depend on what reagents we use. We've also seen other reactions that we make alcohols in, right? So if we consider our addition reactions, if we had an alkene, right, carbon-carbon double bond, we could hydrate that alkene, right? So hydration was adding an H to one side of the double bond and OH to the other. That would produce an alcohol, right? Because again, the OH group is the functional group for alcohol. Depending on the product we wanted, depending on what reaction. So we had a couple different reactions for hydration of an alcohol or hydration of an alkene. The first one was that acid catalyzed hydration, right? So if our alkene didn't have any possibility of carbocation rearrangement, we could use dilute acid to hydrate it. Again, we would get the Markovnikov product here, right? So again, depending on what type of product we wanted. If we use acid catalyzed hydration, we would get the Markovnikov product as a result. If our alkene was potentially able to undergo rearrangement, we would not usually want to use that acid catalyzed hydration. If we wanted the exact same Markovnikov product, instead we would preferably use that oxymercuration demercuration reaction, right, where we used mercuric acetate. We used water as nucleophile, and then we reduce that mercuric acetate off using sodium borohydride. Again, this was for alkenes that would undergo carbocation rearrangement. If we utilized acid catalyzed hydration, this was always the smarter way to go. We'd get the Markovnikov product. And then finally, if we wanted to produce an alcohol that was the anti-Markovnikov product, so anti-Markovnikov, we would have to use the hydroboration oxidation reaction, which was that BH3 and THF in a first step, and in a second step, we'd oxidize the borane off with the hydrogen peroxide and sodium hydroxide. So again, these are three separate reactions that are going to produce alcohols. Which one you want to use depends on what you want to make. Do you want to make the Markovnikov product? Is there a potential for rearrangement? Do you want to make the anti-Markovnikov alcohol product instead? So again, depending on which one you want to use, it's going to depend on which reaction you're going to utilize. Okay, so then we're going to talk about a new way to make alcohols. So this is a new reaction that deals with the reduction of carbonyl compounds. Okay, so before we talk about reduction, we're going to go back. We're going to kind of take a step back a second, and we're going to discuss what reduction means in terms of organic chemistry, as well as what oxidation means in terms of organic chemistry, okay? So anytime we're dealing with reduction or oxidation, we call these or abbreviate these guys redox reactions. And again, in a redox reaction, what we're looking at is the actual movement of electrons between reactants, right? So this is something that ideally you learned back in general chemistry in 151, 152. All right, so in 151 and 152, we discussed redox reactions, and we discussed how we would know whether or not we were dealing with a redox reaction by assigning oxidation states to things, right? So in 151, 152, we learned how to assign oxidation states in terms of inorganic type reactions, right? And we went through all these various rules, and again, the whole idea behind oxidation state is that it was going to help us track electrons to know whether or not they had been transferred in a reaction, to know whether or not a redox reaction had occurred, whether or not something had been oxidized or something had been reduced, okay? Now, unfortunately, in organic chemistry, we can't utilize those same rules because we're dealing with all organic compounds. So we're going to learn how to track or assign oxidation state in organic compounds so that we can actually track electrons in these organic reactions and determine whether or not something has been oxidized or reduced, okay? Now, as a reminder, oxidation state is a fictitious kind of charge, right? It's a fictitious number, fictitious counting mechanism that's essentially just going to be utilized as like a bookkeeping system. Very similar to how we used formal charge when we learned about formal charge in the first semester of organic chemistry, right? So just as a reminder with respect to formal charge, let's say that we had something like methanol here. So let's say that I'm going to go ahead and draw out methanol. And I start with formal charge because it's very, very similar to how we actually track oxidation state or how we're going to assign oxidation state in compounds, okay? So if I said, okay, I want you to calculate the formal charge of carbon, right? To do that, you would say, okay, well, how many valence electrons does carbon have? So if you looked up on the periodic table, you'd find carbon is in column 4 of the main group. So it has 4 valence electrons. And then what we would say is, okay, well, we're going to go in and we're going to homolytically cleave all of these bonds, right? So if we homolytically cleave all of these bonds that carbon is attached to, then essentially, in a homolytic cleavage, one electron goes to one atom, the other electron goes to the other, right? One electron goes to one atom, the other electron goes to the other, so on and so forth throughout the compound, okay? Now, when we homolytically cleave those and we say, well, how many electrons does carbon have? Now we're just going to go around and say, well, we have one from this bond, one from this bond, one from this bond, one from this bond, right? So the number of valence electrons is how many the atom wants, right? So carbon wants 4 electrons. When we homolytically cleave all these bonds around carbon, it gets 4 electrons, right? So the formal charge of this carbon is 0, okay? All right, so again, that's a reminder of how we've really calculated formal charge thus far. Now, what differs with respect to oxidation state? Okay, so now we're going to go over here. We're going to talk about same exact compound. So we're going to talk about methanol. How are we going to track or how are we going to calculate the oxidation state for carbon, specifically in methanol? Okay, so now, same thing, right? We're going to say, well, how many valence electrons does carbon want? Carbon wants 4 electrons around it, okay? Now what we're going to do is we're going to heterolytically cleave all these bonds, right? And so to do that, what we're going to do is we're going to give the more electronegative atom in the bond all of the electrons from a bond, right? So for example, in this carbon-hydrogen bond right here, to determine who gets those electrons, I'm going to figure out who is more electronegative. Between carbon and hydrogen, carbon is more electronegative, right? So I'm going to heterolytically give all of those electrons to carbon in that bond, right? So for this guy, carbon is going to get both electrons in this bond, right? So we're going to get rid of this bond. Hydrogen is going to get 0 electrons, right? We're going to do that for all of these carbon-hydrogen bonds. So it's this guy. Again, carbon is going to get both of these electrons and both of these electrons, so these bonds are gone, hydrogens are going to get 0 of those, okay? Now, we look at the carbon-oxygen bond, right? So carbon-oxygen bond, we find that oxygen is more electronegative, so because of that, it's going to get all of those electrons and carbon's going to get none from that bond, okay? So now, if we look at carbon, it wanted 4 electrons. When we heterolytically cleave all of those bonds, it ends up with 1, 2, 3, 4, 5, 6 electrons, okay? So we have 6 electrons instead. It wanted 4, it has 2 more, so the oxidation state here is 2 extra electrons, or a -2. All right, so this would be the oxidation state of carbon in methanol. Okay, again, it wants 4 electrons, that's its valence electrons. We heterolytically cleave all of the bonds between carbon and the other atoms. The more electronegative element is going to get all of the electrons in those bonds. And so for all of the carbon-hydrogen bonds, all of those electrons are going to go to hydrogen, whereas for the carbon-oxygen bond, they're going to go to oxygen, right? So we do that, we count up the electrons. Carbon wants 4, because again, this is valence. In this compound, it gets 6. It has 2 extra electrons right? And so that's going to give it a -2 oxidation state. Okay, so that's how we're going to actually calculate oxidation state in terms of organic compounds. All right, so we can do the exact same thing for carbon with different things attached to it, right? So for example, methane. In methane, we've got 4 electrons again that carbon wants, but now all of these bonds between carbon are between carbon and hydrogen, right? So again, if we heterolytically cleave those, carbon is going to get 2, 4, 6, 8, right? Hydrogens are going to get 0 here. If it wants 4, but instead gets 8 in this compound, it has a -4 oxidation state because it has 4 extra electrons than what it really wants, right? So the oxidation state here would be a -4. We just calculated the oxidation state for carbon and methanol. We found that was a -2. So if we move into formaldehyde, again, we're looking at this carbon. We've got 4 electrons that we want. It is going to get 2 from this bond. It's going to get 2 from this bond. But now what we have here between the carbon and the oxygen in this double bond, the oxygen is going to take all 4 of these electrons in this double bond. So carbon's not going to get any. Let me actually do that in a different color. Right, so again, each bond is going to be given entirely to oxygen here because it's more electronegative. Carbon's not going to get anything here. So when we count up all the electrons that we've given to carbon in this compound, we end up with 4. So the oxidation state here in formaldehyde for carbon is 0. As we move on, so we can move to formic acid. Again, the carbon-hydrogen bond, those 2 electrons will go to carbon. But now for the rest of these guys, these are all carbon-oxygen bonds. So all of these electrons are going to go to oxygen, to oxygen. So carbon's not going to get any here. We have 4 that we want. We only get 2 in this compound. So because of that, it has 2 less electrons than it should have. So now we're going to have a +2 oxidation state. So we have an oxidation state of a +2. And we move all the way to the fully oxidized version of carbon. For this guy, again, we want 4 electrons, but now all of these bonds are to oxygen, right? So this oxygen is going to take 1, 2, 3, 4. Carbon's not going to get any. This oxygen is going to take, again, 1, 2, 3, 4. Carbon's not going to get any. So when we look at carbon, it has 0. So 1 and 4 doesn't have any. As a result of that, we have a +4 oxidation state. So the fully reduced version of carbon is something like methane, where it has a -4 oxidation state. The fully oxidized version of carbon is carbon dioxide, where it has a +4 oxidation state. Notice that carbon in our organic compounds can move all the way from -4 all the way to +4. Okay? Okay, so in a reaction, we utilize these oxidation states to track whether or not something has gained or lost electrons, right? So if your oxidation state increases, right? So if your oxidation state goes up, like if we went from a -2 to a 0, that means in a reaction, right, you have essentially lost electrons. And just as a reminder, loss of electrons is oxidation. And if you have trouble remembering that, you can always have Leo says grr, Leo the lion says grr. Loss of electrons is oxidation. Whereas if your oxidation state has decreased, right, if you've gone from a 0 to a -2, right, that means that you've gained negative charge, right? That means that you have gained electrons. Then you've been reduced. Right, so Leo, the lion, says grr, gain of electrons is reduction. Okay, so again, how do we utilize these oxidation states? Well, we can figure out whether or not carbon in a reaction has been oxidized or reduced by tracking the oxidation state of it. If the oxidation state in going from reactant to product has increased, it's lost electrons to somebody else, it's been oxidized. Whereas if the oxidation state in going from reactant to product has decreased, it's gained electrons, it's been reduced. Okay, so let's go ahead and go through an example of how we're going to utilize this. And then I'll let you guys do a problem, and then I'm going to cut it off for today. So we have a reaction here where we take a ketone and we turn it into a diol. So we have a ketone, and we turn this guy into two alcohol, so a diol. And we want to know whether or not this has been oxidized, this has been reduced, or whether it is neither, okay? So what we're talking about here specifically is the carbon here that we're talking about with respect to the thing attached to the oxygen as well as the thing attached to the two alcohol groups, okay? To know whether or not something has been oxidized or reduced or whether nothing has happened in terms of oxidation state, we first have to assign oxidation state to our reactant, right? Our reactant ketone as well as our product alcohol, okay? So I'm going to take this carbon, or I'm going to take this guy down here. We have a carbon. It's got a double bond to methyls. And it's got a double bond to the oxygen, right? And then it's got a bond to each methyl, okay? Again, I'm trying to focus on assigning the oxidation state of this carbon, okay? The first thing I'm going to start with are these carbon-carbon bonds, right? So in our example, we've been dealing with carbon-hydrogen bonds, right? And we said, okay, we'll homolytically cleave those bonds and give the electrons to the more electronegative element. Now we have two bonds between the same atom, right? We have a carbon attached to a carbon attached to a carbon. For these guys, they're going to be splitting those electrons equally because they have the same electronegativity, okay? So for these bonds, we will say that one of them goes to this carbon, one of them goes to this carbon, whereas for this bond, one of them is going to go here and one of them is going to go here. So if you have atoms of the same type in a bond, you're going to split those electrons equally, okay? Now, when we consider this bond, this double bond, right, this is between carbon and oxygen, now you have a bond between atoms of differing electronegativities, and so we are going to split that bond heterolytically. We're going to give all of those electrons to oxygen. We're going to give 0 of those electrons to carbon, okay? And so because of that, all of these guys are going to go up here to oxygen, and none of them are going to go here to carbon. And so now to calculate the oxidation state here, again, carbon wants 4 electrons. In this compound overall, though, we have only given it 2, right? So it wants 4, it only has 2 electrons, so it's deficient in 2 electrons. That means it has a positive 2 oxidation state, right? So we have a positive 2 oxidation state here. Now to figure out if it's been oxidized or reduced, we need to do the same thing for the product. So again, we have a methyl, we have a methyl. I'll go ahead and draw this as a carbon. We have a carbon to oxygen, hydrogen, carbon to oxygen, hydrogen. Let me clear that up in the middle. Okay, so same thing. God damn it. Same thing, all right? I'm going to start with these carbon-carbon bonds. Again, there's no difference in electronegativity here. So when we split these, both carbons going to get 1 and 1, 1 and 1. Now as we move up to these carbon-oxygen bonds, oxygen is more electronegative. So in the single bond between this guy, both of these electrons are going to go to oxygen, and 0 are going to go to hydrogen. Both of these electrons are going to go to oxygen, and 0 are going to go, not hydrogen, pardon me, carbon. And 0 are going to go to carbon, right? So we are splitting these heterolytically. Oxygen is more electronegative. Carbon doesn't get anything. And so at the end of the day, carbon wants 4. It only gets 2 in this compound again. So it has a positive 2 oxidation state. So a positive 2 here, right? So again, if oxidation state has increased, let's say if we went from a positive 2 to a positive 4, that would have been oxidation. If we had decreased a positive 2 to a 0, or minus 2 or minus 4, that would have been reduction. If we go from a 2 to a 2, then nothing's happened, right? So there is no redox process here. That carbon has neither been oxidized or reduced, and the correct answer here is neither. Okay, so go ahead and try some of these on your own. So I want to know, again, whether the reactant starting material has been oxidized, reduced, or neither. And you're going to assign oxidation states to help you determine that. So go ahead and try this, push pause, and then come back, and that will be it for the day. Okay, so we'll go ahead and go over these. So for the first one, A, again, I'm going to go through. I'm going to assign oxidation state to my central carbon here. Now for this guy, we've got a couple of bonds to consider. We have a carbon-hydrogen bond here. So between carbon and hydrogen, carbon is more electronegative. It is going to take both of the electrons in that bond. We have a carbon-carbon bond here. Again, they don't differ in electronegativity at all, so that bond's going to be split evenly. So this carbon is going to get one, this carbon is going to get the other. We'll get rid of that bond. And then for the last one here, we have carbon-oxygen, double bond. Again, oxygen is more electronegative, so it's going to get, I want to do that in black, all of those electrons, right? And carbon's not going to get any of them, okay? So now we have 3 electrons. Again, carbon wants 4 electrons. It gets 3 electrons in this compound, so it has 1 less electron than it needs. So it has a +1 oxidation state. So we'll write this up here. We've got a +1. As we go to the product here, we'll start with the carbon-oxygen bond here between that alcohol. So we've taken a aldehyde. This is important to note too. And we've turned it into a carboxylic acid. And so when we go over here, we've got a carbon-oxygen bond. Again, oxygen is more electronegative, so it's going to take both of these electrons. We're going to get rid of that bond. We've got a carbon-carbon bond. We're going to split it equally because they have equal electronegativity, so we've got 1 and 1. I'm going to get rid of this bond. And then we've got an oxygen-carbon double bond. Again, oxygen is more electronegative. It's going to take all 4 of those electrons, leaving nothing for carbon. And so the only thing carbon has is 1. It wants 4 electrons. It only has 1 electron, so it has a +3 oxidation state, right? And going from a +1, to a +3, we have increased in oxidation state, meaning that, yes, this compound has been oxidized, right? And so I'm going from an aldehyde to a carboxylic acid. That is a good indicator of oxidation. Okay, so move down here. We have an alcohol going to a ketone. Again, we're focusing on this carbon, right? So I'll start. There is a bond here to hydrogen that needs to be emphasized. So we've got carbon. We've got this bond to another carbon. So again, this guy's going to be split equally. We've got this bond to another carbon. So again, this guy's going to be split equally. We've got this bond to hydrogen. Carbon's going to claim all of those guys. And then we've got this bond to oxygen. Oxygen's going to get both of those, right? So if we keep track of this, we had 1, 2, 3, 4. So it wants 4 electrons. In this compound, it does have 4 electrons. So we have a 0 oxidation state. Zeros and O's look the same. So 0 oxidation state. If we go over here to our ketone, again, we're looking at this carbon. So if we divide this bond evenly, we've got 1, 2. But then for this bond, oxygen gets all of these guys. So it gets 1, 2, 3, 4. So here, this carbon only gets 2 electrons. It wants 4 electrons. It only gets 2 electrons. We have a +2 oxidation state. And going from a 0 to a +2, we have increased in oxidation state, which means we have been oxidized. All right, so in moving from an alcohol to a ketone, we find that there is oxidation in those reactions. Right, so long term, we're going to have these trends where you don't necessarily have to calculate the oxidation state of things to figure out whether or not something has been oxidized or reduced. In general, if you move from an aldehyde to a carboxylic acid, that compound's undergone oxidation. If you move from an alcohol to a ketone or an aldehyde, that compound has undergone oxidation. Now, if both of these guys are oxidations, right, as is, then the movement in reverse would be a reduction, right? If we had a ketone and we made an alcohol out of it, we would be moving from a positive 2 oxidation state to a 0 oxidation state. So this would lead to a decrease in oxidation state, which would be a reduction, right? So what we're going to move into is how to make alcohols, right, by taking a ketone and reducing it, right? So another way to prepare an alcohol is by taking a carbonyl containing compound and reducing it with a reducing agent to produce our alcohol. And that's what we'll move into next, but we'll move into that next week.